All right. Our next speaker is Quentin Anthony from he's a PhD student from Ohio State University. He's studying in Dr. D.K. Panda's network-based computing lab, and kind of his research interests are in applying MPI for GPU systems with a focus on deep learning. So he's going to give a talk today on applying a Summit supercomputer, which is a supercomputer at the Oak Ridge National Labs, to a challenging problem of image segmentation. Quentin?
Okay, thank you for the introduction. As you said, my name is Quentin Anthony. My co-authors are Ammar, Awan, Arpan, Jain, Subramoni, and my advisor, Dr. D.K. Panda. All of us are in the network-based computing lab. So I'll be talking today about training efficiently semantic image segmentation models on Summit using Horovod and MVAPICH2 GDR. So first I'll introduce sort of the state of the field and how accelerators relate to my work. And then I'll get into the background of how the software stack works together, and the challenges that we faced in this work, and then the methods that we use to solve them, and then the results we have at the end. So deep learning is possible now due to the availability of large data sets and powerful accelerators. So we have the top 500 accelerator market here. Most of it's dominated by NVIDIA V100s, as you can see. So the ImageNet Challenge is a prime example of the state of GPUs in deep learning, with about a 90% adoption rate in 2014. So deep learning frameworks like TensorFlow and PyTorch allow users to implement and experiment with deep neural networks. These frameworks hide most of the complicated details like backpropagation and provide an interface to define DNN models quickly and easily. We'll be focusing on TensorFlow in this work because the segmentation model, DeepLab v3, the research there is performed by Google. So most frameworks are optimized for NVIDIA GPUs, so we'll be using Volta 100s in our work. And then distributed training support is still in its infancy. So all the deep learning frameworks have their own distributed support, which is not standardized. So Horovod is a middleware that we'll discuss that standardizes distributed training for us. So now I'll go into the background on distributed DNN training and how it's applied to semantic image segmentation for our work. So for distributed deep neural network training, we have relies upon deep neural network training, which consists of two phases. So in the forward pass, the DNN makes a prediction based on the input, and this prediction is compared to the actual output to get the error. And the same error is used in the backward pass to calculate the gradients and update the weights of the model. So this is one iteration of training for the given batch size, and this process is repeated until we cover all the images in the dataset. One pass over is an epoch, and we usually typically need about 100 to 1,000 epochs for efficient training. So training is such a compute-intensive task due to the large data sets and complex deep learning models that are on the market. So MPI-driven training is on the rise for HPC systems to speed this training up. Broadly distributed DNN training is split into three approaches. So data parallelism is the focus of this paper, and it's when you split a full replica of the DNN model across each machine in the system, and then you split the data among them. And then model parallelism is splitting the model among the machines of the system and then not splitting the data. And then hybrid parallelism would be splitting the model among each machine and then splitting the data among multiple machines. So we'll be focusing on data parallelism for semantic image segmentation. We use MVAPICH2 GDR, which is a MPI library designed for NVIDIA GPUs over Mellanox InfiniBand adapters. It's based on MVAPICH2 and provides support for both x86 and open power systems. There's support for many NVIDIA GPU features with CUDA, including non-blocking collectives, CUDA managed memory, GDR copy 1.0 and 2.0, and then the focus here will be on the large message collective designs for DL frameworks. More information is on the user guide if you'd be interested in learning more. So Allreduce is the main bottleneck for distributed DNN training with data parallelism. It's a generic communication pattern in the MPI standard, which allows basic element-wise operations like the sum to apply to all the participating processes in the group. So standard data parallel distributed DNN training uses an all-reduce operation to synchronize the update gradients across different workers. Several optimization strategies are implemented in Horovod, which is our data parallel middleware, to optimize the DNN training performance by hiding all reduced costs behind computation. Horovod can be configured with MPI, IBM's DDL, Facebook's Glue, and Nickel. So semantic image segmentation is a problem that we wanted to solve here for distributed training. It requires the classification of each... I'm sorry? Okay. It requires classification of each pixel. So examples for new problems include autonomous driving, medical imaging, and climate analysis, which motivated this problem is the one we solved. So it requires a mapping to each pixel to an object class, as you can see in the figure here, which is an example data sample from the Pascal segmentation dataset. And they typically contain larger images, 513 by 513, than image classification. And they're typically more compute intensive than ResNet 50, which was our motivating example here. So we compared ResNet 50, which is a classification model, with DeepLab v3 Plus, a segmentation model, on a synthetic benchmark with a single V100 GPU. First, we increased the image size to 513 by 513, and we saw throughput decrease as expected. Then we compared, on the same image size, a classification model to a DeepLab model, and we noted that DeepLab requires significantly more computation per image than ResNet for the same image size. So since segmentation models require so much computation per image, they're prime candidates for HPC systems. So you can see here that we get about 60 to 70 images per second for a classification model, ResNet, compared to about a 6 image per second for segmentation. So it's about a 10x slowdown. So we use Horovod to distribute DeepLab v3 on Summit. The Horovod is a distributed DNN training framework that employs data parallelism and acts as a middleware between the DL framework, in this case TensorFlow, and the communication backend, in this case MVAPICH2 GDR. Its performance is strongly dependent on the all-reduced performance of the backend. So Horovod uses a technique called tensor fusion to accumulate small all-reduced operations. It works by selecting update tensors that fit into a buffer, where the user sets the size with Horovod fusion threshold, and repeatedly selects tensors within the cycle time, which is also set by the user, the cycle time. We demonstrate in this paper that these parameters should be tuned to improve training performance, especially for novel DNN workloads like semantic image segmentation. So the full program stack is that Horovod provides a standard implementation of data parallel training. We have DeepLab at the application side, and we have our deep learning framework, in this case TensorFlow, and then Horovod is able to act as a middleware between MPI and the DL framework. An added benefit of Horovod, as a note, removes the requirement to build the DL framework from source for MPI support. So you can have your own non-distributed DL frameworks, PyTorch and TensorFlow, for example, and then install Horovod on top of them and plug and play. So next we'll investigate some of the research challenges that we resolve. After adding Horovod support to DeepLab v3 Plus and characterize the performance with both MVAPICH2 GDR and Nickel backends up to 132 GPUs on the Summit HPC system. These backends are compared to ensure that the issues with Horovod and not the communication library. So both backends only achieve around 75 to 80% scaling efficiency, up to 132 GPUs, which is a significant drop from the ideal linear scaling performance we would expect. While other works in this area have changed MPI, Horovod, and the DNN model, and we wish to demonstrate the performance can be significantly improved by simply tuning Horovod appropriately for the novel workload. Therefore, we remove the time and effort necessary for optimizing the entire software stack, and we condense these challenges as the following broad statement. How do we identify bottlenecks in novel DNN scaling, and how can these bottlenecks be resolved by tuning Horovod? So the methods that we use in this paper to resolve this problem is we make the following key contributions. We scale the existing semantic image segmentation model, DeepLab v3 Plus, by adding Horovod support to it. We do this by following Horovod's suggested workflow to add distributed support. We distribute the DNN copies to worker GPUs. Then we wrap the existing training optimizer in Horovod's distributed optimizer. And then we perform hyperparameter optimization at the desired scale to ensure that we don't lose out on accuracy. We then profile the distributed training with our internal development tool. And the bottlenecks from our profile allows us to perform a grid search tuning of both the cycle time and fusion threshold so that we can fill the fusion buffer at each scale. So with the tuned Horovod at each scale, we perform hyperparameter tuning again to ensure accuracy is maintained. And at the end, we demonstrate that we have significantly improved training throughput without changing the underlying structure of Horovod, MPI, or the DL model. So this is how we tuned Horovod. We set the fusion threshold and cycle time at the runtime with deep lab training and measure the throughput for the first few training steps. We did this for each possible value of the fusion threshold and cycle time, and then found the best throughput through that in a grid search pattern. So an example of setting the fusion threshold and cycle time is depicted here for MVAPICH2 GDR. You just pass these parameters to the training script. As an aside, Horovod, since this work, has added support for auto-tuning its parameters via Bayesian optimization with an auto-tune parameter. It's more generalizable than grid search. And auto-tune can be launched in both Horovod's MPI wrapper launcher Horovod run or directly at runtime with MPI. So next we'll characterize the performance improvements after explaining the evaluation platforms and software libraries we used in the study. We performed these experiments on the Summit supercomputer at Oak Ridge National Lab. It's the #1 ranked on top 500 right now. It has 4,608 compute nodes, and what matters for this study is that we have 6 NVIDIA Volta GPUs per node. And they're interconnected with 2-lane NVIDIA NVLink, which provides 50 gigabytes per second bandwidth. And then the nodes are interconnected with InfiniBand EDR. This would be a diagram of a Summit node architecture. Each node has 2 IBM Power 9 CPUs, which are connected, which are connected to 3 NVIDIA Voltas each. For software, we used TensorFlow 1.14 with MVAPICH2 GDR 2.3.3, and then we ran Horovod on the publicly available Deep Lab GitHub model. So next we'll get to the scaling results for the tuned Horovod system. The metric for comparison we use here are the throughput and the scaling efficiency of Deep Lab training. The scaling efficiency is the actual experimental performance divided by the ideal performance here. So we want to get as close to 100 as possible. Typically 90% is what we're shooting for here. We were able to see a 23.9% improvement in scaling efficiency, which is significantly improvement for only tuning Horovod. We also studied the throughput, which we measured in images processed per second. We see about a 1.3 times improvement in training throughput. So in order to understand why this improvement is happening, we profiled the tuned and default Horovod training runs. We applied our internal profiling tool HVProf, which you could find more on here, to profile all reduced before and after tuning Horovod. We can see that most of the update tensors are pushing up against the default Horovod threshold boundary, which is about 64 megabytes for the default training runs. But after running tuning, we were able to more efficiently spread the tensors. So if we fill the fusion buffer every single training step, we can more efficiently use the system and not use such wasted space. Also, if we push up to the higher message ranges, we can take advantage of MVAPICH2 GDR's large message collectives. So we also measure the performance improvement at each message scale for both the tuned and the default Horovod runs. Since we're providing more room in the fusion buffer for smaller tensors, we reduce the number of calls in the small message range where the fusion buffer is not full. We also see more improvement as message sizes increase due to MVAPICH2 GDR's large message designs. So we can effectively push the messages up in the hierarchy. We were able to see about a 68% improvement in the total all-reduced time after tuning Horovod parameters. As in conclusion, semantic image segmentation is a new deep learning problem that requires more computing power than conventional image classification. Novel DNN architectures bring about novel communication bottlenecks, and these can be solved by profiling and then tuning your middleware. In order to identify and resolve the bottlenecks in DNN training, a detailed profile should be used. In order to achieve near linear scaling for novel DNNs, we don't need to change MCI, Horovod, or the DNN model significantly to achieve better performance. Instead, we may be able to tune the DL framework middleware, which is Horovod in this case, to provide near linear performance. Finally, we don't sacrifice segmentation accuracy at scale. We're still able to achieve about 80% mean intersection over union after hyperparameter tuning at 132 GPUs, which is competitive. In the future, we could apply other novel DNN models with bottlenecks that could benefit from middleware tuning. We could also use Horovod's auto-tune feature and evaluate the Bayesian tuning. Also, now that we have a scalable segmentation model with competitive accuracy, we can easily apply it to other interesting data sets, such as pathology or climate. So thank you. Are there any questions?
Yeah. Any questions for Quentin?
Yeah, I have one question. So you were talking about in your summary slide in the beginning, you were saying that you tune the Horovod's parameters, and then you did hyperparameter tuning to maintain that you are not losing any accuracy.
That's
But
correct.
I don't understand that why hyperparameter tuning should be dependent upon Horovod's parameter tuning, because Horovod is just for computational reasons you are doing, and it should not affect the accuracy of your or the convergence of your algorithm.
So Horovod handles some of the basic, like your learning rate scaling for the optimizer, for example. But there are model-specific hyperparameters that still need to be tuned in this case.
Right, but that is that independent? Is that dependent on what parameters you tuned for Horovods, or it can be done independently?
Yeah, it needs to be. They're separate from the parameters that Horovod
Yeah,
has
so
control of.
and they, I mean, they are not sensitive to the choice of thresholds that you set for Horovods, right?
That's
Because
correct.
one is dealing with computational performance and one is dealing with more convergence issues, right? So it is an
Yes.
independent thing. Yeah, okay. Yeah, okay.
Any other questions? I have one. So you kind of touched this on your future work, but now have you thought about applying this to other kinds of DL models, including like language models, RNNs, LSTMs? Do you think like the structure would have to change for those?
Absolutely. I think that transformer models and video models in particular could really benefit from this because it's the large message ranges that we need to fuse together. So that's something that I'd be interested in applying to. But in any distributed DNN training, if you tune your middleware, I think you can get much better performance.
Right. Okay. Any other questions? Thanks, Quentin. So we're into our break right now. We've eaten